Have you ever wondered why you can't see the air around you, even though it's everywhere? It's a question that seems simple on the surface, but the answer reveals something fascinating about how light and matter interact. Today, we're going to explore the logic behind transparency and why certain things are invisible to our eyes. If you're curious about the physics that shapes our everyday perception of the world, subscribe to the channel so you don't miss out on more explorations like this one. Let's start with the basics. Light is the key to everything we see. Your eyes don't actually see objects themselves. Instead, they detect light that bounces off objects and travels into your pupils. Without light, there'd be nothing to see at all. Air is made up of tiny molecules, mostly nitrogen and oxygen, that are spaced far apart from each other. These molecules are so incredibly small that they barely interact with visible light at all. When light travels through a material, one of three things can happen. The light can pass straight through without being deflected. We call this transparency. The light can be absorbed and converted into other forms of energy, like heat. Or the light can be scattered in many different directions. Air is transparent because the molecules that make it up are simply too small and too far apart to scatter visible light in any significant way. Now here's where it gets interesting. Imagine light as a wave traveling through space. When a light wave encounters an object, the size of that object relative to the wavelength of the light matters enormously. Visible light has wavelengths ranging from about 400 to 700 nanometers. A nanometer is 1/1000th of a meter. The nitrogen and oxygen molecules in air are roughly 1/10th of a nanometer in diameter. They're much, much smaller than the wavelength of visible light. Because these molecules are so tiny compared to light waves, the light essentially passes right by them without noticing they're there. It's like ocean waves rolling past a grain of sand on the beach. The grain is far too small to disturb the wave's motion. However, if that grain were the size of a boulder, the wave would crash against it and scatter in all directions. The same principle applies to light and air molecules. But wait, you might be thinking, what about things like fog or clouds? You can definitely see those, and they're made of water and air. The difference is crucial. Fog and clouds contain water droplets, not individual water molecules. These droplets are much larger than the wavelength of light. When light hits these droplets, it scatters significantly. That's why you can see fog and clouds. The water droplets scatter light in all directions, and some of that scattered light reaches your eyes. This is where transparency breaks down. Let me clarify something important about light scattering. Scattering doesn't mean the light disappears. It means the light changes direction. When light is scattered, it bounces off particles and travels in new directions. If light is scattered uniformly in all directions, you won't see through the material clearly. The material becomes opaque or translucent. Air is transparent because scattering doesn't happen significantly in it. Now you might be asking yourself, if air molecules don't scatter visible light, what about ultraviolet light? Ultraviolet light has much shorter wavelengths than visible light, typically between 10 and 400 nanometers. Because ultraviolet wavelengths are smaller, they interact more readily with air molecules. Some ultraviolet light does get scattered by the atmosphere. That's actually why the sky isn't completely dark above us. But that's a story for another time. What matters here is that the size of the wave relative to the particle determines whether scattering occurs. Like this video so far, because we're diving deep into why the world looks the way it does. Let's explore this concept further by thinking about other transparent materials. Glass is transparent to visible light for a similar reason, though the explanation is slightly different. Glass is made of silicon dioxide, and its atomic structure is arranged in a way that allows light to pass through it without significant scattering. The electrons in the glass absorb the light energy momentarily and then re-emit it in the same direction, a process called refraction rather than scattering. The key is that the material structure doesn't disrupt the light's path in a random way. Water is another great example. Pure water is transparent because water molecules are small and organized in a way that doesn't scatter visible light significantly. But when you add sediment or particles to water, it becomes cloudy. The particles scatter light, and you lose transparency. The same water becomes opaque or translucent. This demonstrates that transparency is fundamentally about what happens to light when it encounters matter. There's also something called Rayleigh scattering that happens in the atmosphere, and it's worth understanding. Even though air molecules don't scatter visible light noticeably, they do scatter shorter wavelengths more effectively. Blue light has a shorter wavelength than red light. This is why the sky appears blue during the day. The shorter blue wavelengths scatter off air molecules more frequently than longer red wavelengths. But this scattering is subtle. Most visible light still passes through the atmosphere without being scattered. Air remains mostly transparent to our eyes. The color of objects also plays a role in visibility. An object appears a certain color because it absorbs some wavelengths of light and reflects others. A red ball appears red because it absorbs most wavelengths except red. The reflected red light travels to your eyes, and you see the ball. Air doesn't absorb or reflect visible light in a way that creates color. It's essentially neutral. The light passes through it unchanged, which is why air is invisible. Think about it this way. For you to see something, light must be absorbed or reflected by it in a noticeable way, or light must be scattered by it. Air does none of these things effectively for visible light. The molecules are too small, they don't have significant color properties, and they don't create enough scattering to be visible. That's why you can see straight through the air to distant mountains or the sky beyond. The air itself remains invisible. However, there are situations where air becomes less transparent. Pollution and particles in the air scatter light, which is why smog exists and why air quality matters. When air contains dust, smoke, or other particles, those particles scatter light, and the air becomes hazy. You're not seeing the air itself, you're seeing the particles suspended in the air. This is a crucial distinction. The air molecules remain invisible. It's always the particles in the air that we see, never the air itself. This principle extends to the entire atmosphere. The atmosphere is mostly transparent, which is why we can see the sun, moon, and stars. But when conditions are right and particles are present, the atmosphere's transparency decreases. Pollution, dust storms, and volcanic ash all reduce atmospheric transparency. These are all particles in the air, not the air molecules themselves. Understanding why we can't see air helps us appreciate the elegance of nature's design. Our eyes evolved to detect light, and air, being mostly transparent to that light, doesn't interfere with our vision. This is fortunate, because we need to see through air to navigate the world. If air scattered visible light significantly, the world would be completely opaque, and vision would be impossible. The same logic applies to understanding why certain things are transparent and others aren't. It all comes down to size, structure, and how light interacts with matter. When particles are smaller than the wavelength of light, they don't scatter it. When particles are larger than or comparable to the wavelength, scattering occurs and transparency is lost. This simple principle explains a tremendous amount about the world we see. If you found this explanation helpful and it's clarified why air is invisible, please like the video and subscribe to the channel for more deep dives into the physics of everyday life. I'd love to hear from you in the comments. Have you ever noticed how your perception of air changes when particles become visible, like in fog or dust? What situations have made you most aware of air's presence or absence? Drop your thoughts below and let's explore these questions together.